published paper. So Ben Sherman will tell us how to do solid modeling using exact real arithmetic in a little language they've designed. Thank you.
So solid modeling is about the computer representation and manipulation of shapes. So that could be used for computer-aided design, for designing mechanical parts like this, for computer graphics, and for 3D printing. And so the standard practice here is to define geometric algorithms, basically pretending that we have real numbers, but then using floating point to implement it. And that is unsound. And so here's an example of that. So suppose we have 3 points in the plane, and we want to determine, do they form a left turn, a right turn, or are they collinear? And so we can specify what that means, and we can specify an algorithm sort of with real numbers. But when we implement it with floating point, when we have something that's kind of close like here, it's actually a left turn, but it's really close, it could be misclassified as a right turn or collinear, and this is unsound. And it doesn't seem too bad here because it's only a tiny perturbation. It's really a small error. But what happens is if you use this as a primitive to design a larger algorithm, you can get catastrophic errors, and that's what this slide is showing here. So here we have a convex hull algorithm that's using that primitive. So here we want to find the convex hull of a set of points in the plane. And you can think about that as taking a big elastic band around all the points and letting it contract onto the points, and it's that region that's spanned by that algebra perimeter. So on the right side, we see a catastrophic failure in that we completely miss that point over to the left side. And the reason it does that is because internal to the algorithm, it's using this left-right turn, and it mistakenly does a left-right turn with x compared to some of the other points there in the interior of the convex hull. So this is problematic, and so this talk is really about a sound approach to solid modeling, where we're going to really restrict ourselves to only ways of programming that are sound. And we're going to do that using Marshall B, which is our extension of an existing language called Marshall. And it's a language where all functions are continuous. And so this fixes the left-right turn issue that we had before in one of our favorite PL techniques by making it impossible. But it's impossible for good reason, essentially. The fact that we can't implement it in the language sort of says fundamentally it shouldn't be possible. It's not robust. But another PL wisdom that we can apply is that if we restrict the sort of functions that we can construct, making some things impossible, when we use those functions, we get to assume more about them. And so in this talk, I'm going to describe a new shape representation called krep, which is fundamentally using those new possibilities to compute things that basically are not possible, at least with this level of genericity, with other shape representations. And this is making critical use of the language properties that we have. So using this, we built a library called Stoneworks, which is just a library for solid modeling. Okay, so I'll walk through an example solid modeling task that we'll solve using our framework, and then the rest of the talk will be explaining about how it works, essentially. Okay, so here's a solid modeling task. So oftentimes, we'll construct some shape in a solid modeling tool. Usually, it'll be more complicated than this ideal cone here, but we'll keep it simple for now. And then we might want to produce a mesh, which is a collection of triangles, and this could be useful, for instance, for 3D printing or for finite element methods. But when we produce that mesh, we want to know that it's sufficiently similar to the shape that we started out with. So we might want to verify that we've produced a shape that's sufficiently similar. So this isn't about producing the mesh, but it's about computing the distance between the ideal shape and the mesh in a guaranteed sound way. So what we're going to do is compute the Hausdorff distance. So what I've shown here on this slide, it's both code for computing the Hausdorff distance in Marshall, but it's basically the textbook definition that you would see for Hausdorff distance, for instance, in Wikipedia. So the bottom figure there is from Wikipedia. So just for reading this code here, the script R are the real numbers. This E is a type variable. So you can think of E, basically think R2 or R3, right? The plane or 3D space. So here is the fundamental thing. We're using Kshapes, which is a notion of shapes that I'll define later. But for now, you can just think of them as shapes, subsets, something like that. And so the key aspect is this distance function. It's kind of complicated. It's actually a minimax optimization problem as it's defined here. And the way you can think about the distance is looking at this figure below, is that we can take a point on one shape and we find the closest point on the other shape, and the Hausdorff distance is just the maximum of that quantity over all possible first choices of points. So you can kind of think of it like this minimax optimization game. Okay, so let's do a construction here. The sort of first part of our solid modeling task, we'll just construct this cone. And we're just constructing the surface of a cone, so it'll have two pieces. It'll have the party hat top and a disk base. So to program the party hat top, what we're going to do is we start with this unit interval to parameterize the height along the cone. And then for each point in the unit interval, we're just going to build a circle of varying size depending on where we are. And we'll use compact interval to take the union of all those circles, and that'll give us the party hat. So what you can see here is that these K-shapes actually form a monad. So compact union is the bind and point is the return. So you can think of it as a non-determinism monad. We're just specifying all the points using bind and return here. And so base is just taking the unit disk, a standard thing from the library, and bringing it from R2 to R3. And so you see here we're using a few simple shapes from the library. So it turns out here is just a pictorial description of those shapes. The unit disk includes its interior. The unit circle does not. Both of these are K-shapes in the plane. And the unit interval is kind of special, so it's really important. It's a language primitive, actually. And so a lot of the interesting computation that you'll see goes on here is actually a sort of a consequence of that as the language primitive. Okay, so we've done an example construction, and then the next part of our solid modeling task is to do an analysis. So we want to compute that Hausdorff distance. We want to know that our mesh is sufficiently similar to the ideal shape that we started out with. So we have this function Hausdorff dist. It's just a function from the library, and it's parametric over the distance function underlying on points in the space. So here we're going to use Euclidean distance in R3, and that's implemented in this function dr3. So we just compute the distance between the cone and the mesh, and when we enter this at the REPL, what we get, this is the real number type, and we get, because of the real number interface, we get a stream of approximations. So these are going to have rational endpoints in general, or infinity, and they're going to get finer and finer and finer. And for any tolerance that you can desire, eventually they will get sufficiently that fine. But more importantly, what we know is that all of these approximations are sound. The left sides are lower bounds, the right sides are upper bounds. So already from here we can see the Hausdorff distance is positive, so we know that the shapes are not identical, because Hausdorff distance is only 0 when shapes are identical. And it's also at most 0.28, and so that's useful. We've now got a guaranteed bound on the distance between those shapes. Okay, so the rest of this talk will go how Marshall B works, and then I'll get into the shape representation stuff. So as we've seen, points are just streams of increasingly precise approximations. So here, I'm not going to explain the square root code, we'll get back to it, but here we're computing with it, and we get a stream of approximations. And this is not only true at the REPL at the final stage, but you can really think of intermediate values when we're working with just values, for instance, of the reals, as streams. And so what that means is that first order functions are stream transformers. So here we see the squaring function, and at each stage of time we're just using the approximation from square root of 2. So from finite approximations we can produce finite approximations of the output. Okay, so let's get into the definition of K-shapes. So here we have this type synonym. You can think of it like in Haskell. All right, we see it's the continuation passing style monad, so we can already see it's a monad. So K-shapes are going to be for all quantifiers using this logical type, this script B, which we call the Belknap Booleans. And the Belknap Booleans are just pairs of values from the Sierpinski space, which I'll explain now. Comparison is not decidable of real numbers. That's why that left-right turn algorithm screwed up. So instead of having comparison return a Boolean, we get a Sierpinski space. And these are just semi-deciders. So this fact is true, but it's not obviously true. It takes a bunch of computation of square root 2 to see that it is true. So at first we get question marks, and then eventually we get top. Yes, it's true. And in general, we'll eventually get a top in the REPL if it is true, but if it's false, we'll just get non-termination. Okay, so we have true, we have false, which is non-termination, and then we can combine these with and or. So think the ands of two semi-deciders, we wait for both of them to halt, produce a top, and then we can produce a top as well. Okay, so the key thing to notice here is negation is not possible, and that's really annoying, that's problematic. And basically you can think of it as a halting problem thing. I can't take something and know if it's going to be question marks forever or not, and then try to flip it and produce something that halts. Okay, so what are we going to do about this issue? Let's add in a formal opposite. So the Belknap Booleans do exactly this. We have one to represent what it means to be true, and one to represent what it means to be false. You can also think of these like proofs and refutations. So here we have a richer comparison function here than what we saw before. So there's kind of three possible values here when you think about it. Sierpinski had 2, so Belknap Booleans kind of have 4, and this explores 3 of them. On the left side, we have something that's true and not false. 0 is less than 1. On the right-hand side, we have the opposite. It's false, so is false is true, we get the top, and is true is question marks, meaning it's false. And in the middle, we have something that's kind of neither true nor false, and you can think about this as non-termination. We're getting question marks, and we never know when we're looking at it at the REPL. Maybe one of them will turn to top. We don't know, except we can look here and we know the true answer will be question marks forever. Okay. So now we can define the Boolean operations, all the Boolean operations on these Belknap Booleans. So the key thing is now we have negation. We just swap the meaning of true and false. And you can see if I do it twice, I get the same thing back again. So now let's look at and. X and y is true if x is true and y is true. But x and y is false if x is false or if y is false. And so it turns out from the structure of the Sierpinski space, these semi-deciders, this is the unique way of defining the Boolean operations on the Belknap Booleans. And it turns out you can reason about these pretty much like you would a Boolean algebra. It's pretty close. Negation is just a little weaker. So a Boolean algebra would have the red law, where a quasi-Boolean algebra has the blue set of laws instead. So it's a little bit weaker for negation. All right, so if I've constructed these Belknap Booleans, what can I produce useful with them? I can produce real numbers using a Dedekind cut. And so what that allows me to do is to define a number by what it means to be less than that number. So let's do square root, that example that we saw earlier. Well, when is q less than the square root of x? It's less than the square root of x if it's less than 0, or if when I square q, it's less than x. And that gives us a computational way of doing it. So Dedekind cut is a primitive. Not going to explain it here. You can see the paper. But for intuition, you can think bisection. Okay. So now that we've got to the Belknap Booleans, here we are. We can get to our definition of K-shapes. So let's start with the absolute simplest K-shapes, the empty shape. So these are going to be for all quantifiers. So what I need to do is take in a predicate on the space, the underlying space E. Again, think E is R2 or R3. And produce a Boolean value. So here, when does P hold of no points? Well, when does P hold for everything in the empty set? Well, always. So we return true. Easy enough. Okay, so now we can do point, that return of the monad. When does the predicate P hold of the shape that includes just the single point x? All we have to do is apply P to x. And then, so there's another simple shape, like unit interval. I'm not going to explain the implementation, as I mentioned, but we can specify it axiomatically, right? So this is going to be when it receives a predicate P, I have to describe both sides of the Belknap Boolean. So it's true if applying P to any point between 0 and 1 would have returned true, and it's false if there exists some point between 0 and 1 such that I get false. And so basically this is along the lines of what it means really to have a K-shape as a for-all quantifier. Okay, so what can we do with K-shapes once we've constructed them? So we can compute the for-all quantifier with these Belknap Booleans. That's simple because that's the definition of what the shapes are. But more surprising, perhaps, is we also get the existential quantifier for free, and this holds from the relation between existential and universal quantifiers that we expect of Boolean algebras that we also get for quasi-Boolean algebras. Okay, so we can do disjunctive Boolean constructions. We already saw empty. How about union? So when does the predicate P hold for the union of the shapes K1 and K2? Well, I just check that P holds for everything in K1, and I need P to hold for everything in K2. So now I've described the union by describing that for all quantifier. So we also get the monad. So we've already seen point. Let's do compact union. Well, that looks a lot like union, except instead of having two things I'm unioning, I have an index family that's indexed by a compact shape, a K-shape. And so all we have to do, instead of doing the AND of those two things, we'll do a for all over the K-shape that's indexing all the shapes that we're unioning. So again, think back to that party hat, where K would be the unit interval, and then the F would produce all the different circles. So we can construct the unit disk, for instance, and we use that for the base of our cone. So first we construct the unit square as a product of these intervals. And then the unit disk is kind of interesting here. So we say P holds everywhere in the unit disk if this predicate holds everywhere in the unit square. And this predicate basically says, if I'm inside the circle, then I require P to hold. And if not, then I don't need P to hold. So that arrow there is Boolean implication. Works well for the Belknap Booleans. We just define A implies B as not A or B, as we're used to with Boolean algebra. All right, so here we are. Let's get back to this sort of original example, Hausdorff distance. So the key thing to see here, right, about understanding how this computes is understanding the optimization functions. And so now we can sort of see that we have a lot of computational information from using these K-shapes. And again, a lot of that can draw from sort of, it's like a quantifier calculus, and unit interval plays heavily into this. So how do we implement sup and inf over K-shapes? All right, so here's the type signature of inf and the definition. It's only a two-line definition here. So we describe the infimum by describing what it means to be less than the infimum using Dedekind cut. So when is Q less than the infimum of the shapes? Well, it's less than the infimum if for all things that I would pick from the shape, I'd get something larger. And then sup is just really the dual of this. It's almost exactly the same, we just use exists. I'm less than the sup if I can find a single thing that's bigger than I am. Okay, so there we go. With this, you kind of get a flavor of how we can construct K-shapes in a fairly flexible manner, and then also consume them, for instance, doing things like Hausdorff distance. So there's a lot more things in the paper, unfortunately, that I don't have time to get to within this talk. But so I think this talk was ostensibly about solid modeling, but really it's more broadly about exploring how to program soundly with continuous values. So I think it's interesting to explore how to program in this way. So we've seen, first of all, we get soundness, which is great in comparison to things that are not sound. But we also get robustness. So you can think of robustness as being, if I have like an unobservable change in the input, I get at most an unobservable change in the output. And that's essentially continuity, but it's a nice property to have. And moreover, we see that just by having soundness, we don't have to be just negative people saying, no, you can't implement certain things, which we do. But it also allows us to compute other things, such as these higher order functions for optimization, like we saw with sup and inf. And similarly, we can do things like integration. Thank you.
Okay, I'll do it online first, and then. With a number of questions from one Andre Bauer. Do you support the limit operation? So can you take a Cauchy sequence and return its limit?
No, we should. It would. So just sort of the underlying implementation of Marshall doesn't make that simple to do, but certainly with the operational semantics that I presented, it makes it clear how you could take a limit. It wouldn't be necessarily efficient, but none of the things in this language are necessarily efficient.
I'll just take one from the floor. Yeah, this one, yeah.
do you require your meta language to have a non-termination, or are all these stream producing function you're dealing with productive?
Do you require the meta language to have non-termination?
Yes.
So when you mean meta language, you mean the
like
implementation
arrows,
language?
Like all the arrows that you're writing in the in your modal, are they living in, say, Haskell, or could you take ACTA and something that provably terminates?
So the Marshall language is essentially system F plus a bunch of primitives, none of which look like recursion. So you can't program non-terminating functions in Marshall. Does that answer your question?
More or less, yes.
Okay.
Another online one. So there's a number of questions about these Belknap Booleans. So one complaint, you shouldn't call them Boolean, because they're not.
That's a good complaint. I'm happy to hear better names.
But what is the status of true-true? Does that ever come up?
So true-true can be useful in some situations. It kind of represents a non-deterministic decision that you might want to have. So what's sort of annoying in some cases is, so there's another representation of shapes that I didn't have time to go into called OREP, where basically you just define a shape as, you say yes or no, are you inside the shape? But that means on the boundary you do non-termination. But you can do this thing where you sort of make it sometimes say yes and no near the boundary. Yes, I'm in the shape, and no, I'm also outside the shape. And that'll make it, you can kind of take non-termination that would happen there and convert it into non-determinism. And that can be useful. For instance, we have an example in the paper where we compute a depth map to a shape, sort of like a part of ray tracing, I would say. And the thing is, if I shoot a ray that would be tangent to the shape, it actually results in non-termination. But if I fuzz out this shape to be non-deterministic, then I can ensure termination. Even though, I mean, again, in a certain sense, it's not sound that you've done that, but you've specified exactly how unsound it can be with the extent of that non-determinism.
I think there's a question over there.
Is there a relationship between what you're doing and negative translations from classical logic to intuitionistic logic? The for all translation that you showed looks like the Kuroda negative translation, and the other thing that you showed with the double negation of A is equal to A looks like Levenko's negative translation.
So I'm not familiar with the negative translation. I'm not sure of a connection. So here it's, you sort of get some properties holding because it's a De Morgan algebra. So one thing that I have heard of that this is similar to is something called like Chu constructions in linear logic. And basically where you have something and you take a formal opposite and you manipulate things in that way.
Also, is there a reason you call them Booleans and not propositions? Because again, this reminds me of intuitionistic logic because you have true, false, or unknown.
So in a certain sense, right, so we don't have the normal laws that we have of intuitionistic logic. The quasi-Boolean algebra is just sort of distinct. I don't think either one subsumes the other. But definitely it's a less than ideal name. Belknap quasi-Booleans, I guess, could be. I don't know.
I think he calls them B4. So there's two competing questions on Slido at the moment from opposite perspectives. So I'll go for the theory one. Any connection with cohesive homotopy type theory? Or in general, like integrating this into theorem provers, so you can actually reason about the shapes as well as compute with them?
So that's an interesting question. So definitely, basically, the underlying theory of this is you take sort of like, you take a generalized category of spaces, and it's easy to take that to be a topos, and then you can do theorem proving with that. In terms of cohesive homotopy type theory, so I think certainly there's that homotopy part. Now the cohesive part of that type theory, I think, is essentially like a topos for like continuous programming in this sense. So I think they're connected, but I'm not super familiar with it.
You already mentioned that Marshall is not maybe terribly efficient, but can you give kind of like ballpark figures of how far off this is from computing with floating point numbers?
With what numbers?
Well, conventional floating point computation?
So it's pretty far off. There are a few. There are a few sort of numbers in the paper. Just so the example in the beginning there, it takes a few hours actually to produce those results from the REPL. But I think more, this was about designing the abstractions of figuring out what was possible. And I think in terms of efficient computing, first of all, there's a lot of low-hanging fruit. There are some things where it's obvious and we just didn't implement it, like optimizations that would be easy. Now, once you get beyond that low-hanging fruit, there's probably still a large gap of maybe higher-hanging fruit, and then just core hard problems. So I think, like, for instance, this Hausdorff distance formulation involves like minimax optimization, and I'm sure it's possible to encode really nasty problems within that.
Thanks.
Okay, kind of a silly PL question, which is you write your code with explicit continuations, out of the design of the operators, but we might want to present that in a more direct style. So have you tried like having a comprehension syntax or some way to, or just some form of monadic syntax to make the program look a bit less indirect?
So are you thinking, like, would monad syntax be a comprehension syntax? Yeah, certainly it would be a good thing for future work. Yeah, that's certainly syntactically possible. Yeah.
Okay, I think we'll finish with a yes/no question from online. Can you compute the convex hull of a set of points in your language?
Yes. So you wait, just there's clarification that should go with this. I don't want to. So it's in a different sense from the points there, and certainly a different algorithm. So I think it's very interesting in its own regard. So you can compute the convex hull of Kshapes in Rn. And so the code actually depends on the dimension of the n. Again, not necessarily efficient, and not necessarily giving you the same computational interface that you would see for the convex hull algorithm that you saw earlier. So just some caveats to go with that, but yes.
Thank you. And we resume at 3:20.